Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary to the CCQTA and Principal Consultant at Omnicon Consultants. This is our first episode on hydrogen sulfide in crude oil. In this episode, we're going to start with the basics of H2S. Then I'm going to give you a little background on why the CCQTA got involved with H2S in crude oil. Then we'll talk about the various methods that are involved in sample collection and measurement. And lastly, we're going to look at the H2S control methods and how they impact crude oil. Let's start with the basics of H2S so we're all on the same page as we get further in depth on this topic. Firstly, what is H2S? Why is it a problem? And where do you typically find it? And lastly, I want to touch on the definitions of sour and sweet as it applies to oil and gas. H2S is simply the covalent or molecular bonding of hydrogen and sulfur. This is a 3D representation of H2S showing the lone pairs of electrons that cause the hydrogen geometry relative to the central sulfur atom. The lone pairs also give the molecule polarity, which impacts its reactivity and behavior. Let's look at the physical properties of H2S. It is normally encountered as a colorless gas. It has a characteristic rotten egg smell at low levels. However, at higher levels, it can quickly impair your sense of smell, so it's not detected. The density is 1.19 relative to air, so this means that it's heavier than air, so it tends to accumulate in low areas. With sufficient concentration, it is highly toxic on inhalation. It is also highly flammable with a flammable range between 4 and 46 volume% in air. It is also soluble in both polar and non-polar fluids such as water, crude oil, emulsions, etc. And when it's dissolved, it tends to be released if the fluid equilibrium is disturbed by agitation. Let's focus on the toxicity and the flammability aspects for a moment. First, let's talk about the toxicity on inhalation. This table shows the impacts of H2S and highlights the time component of exposure. As you can see, with increasing exposure time, the severity also increases significantly. At 10 ppm, a person can work in that environment for up to 8 hours without any adverse effects. At 20 ppm, you'll start to have irritation in your eyes, nose, lungs, and throat. Between 50 and 150, you will lose your sense of smell and the irritation will be severe. Between 300 and 500, you may be rendered unconscious and could die if left in that environment for 1 to 4 hours. Lastly, at greater than 700 ppm, you'll be immediately knocked down and it may be fatal. This second chart gives a good visual representation of concentration versus time, resulting in health impacts. The back-slanting red lines show the effective time at a given concentration. The higher the concentration, the greater the severity with increasing exposure time. There needs to be some additional context to this to avoid some common misinterpretations. When we speak about the toxicity limits, we are really talking about the volume percent of H2S in the breathable environment. Let's look at two different scenarios. Scenario 1. If you're in an industrial setting, such as a pipeline, refinery, truck terminal for loading and unloading, that likely means there's an exposure risk from an unexpected release. In that case, the whole breathable environment may have H2S at or above the occupational exposure limits. Say a failure occurs in a pipeline and the released fluid contains a high level of H2S. Given that the source is, for all intents and purposes, unlimited, the environment in the immediate atmosphere will readily exceed the exposure limits and would be a great risk to life and health, as this poor fellow just experienced. In this case, maybe a little PPE would have been helpful. Scenario 2. In a laboratory setting, a 1 liter crude oil sample is received. It has a warning that it contains 100 ppm of H2S. Some people look at that number and remember their H2S safety training and immediately assume it will be toxic to handle. What is often overlooked is that the H2S source, in this case the sample, has a finite quantity of H2S. In this scenario, the total volume of H2S in the sample is approximately 0.05 liters. Say that the sample was spilled and all the H2S was released into the lab environment. That 0.05 liters of H2S now mixes with the volume of air in the lab. A room with the dimensions of 10 by 10 by 8 contains approximately 23,000 liters of air. Therefore, 0.05 liters of H2S is diluted into the air, and for a total concentration of 2 ppm in the environment. Not really a risk to life and health, although easily detectable by smell. This is not to say that precautions should not be taken, since dilution from the point of release will take some time, so persons near release may have immediate higher exposure than those further away. Now let's look at H2S from a flammability perspective. This plot shows the flammable zone for H2S in air. The red zone shows that H2S is flammable in air between 4 and 46% by volume. Below 4%, there's not enough fuel to support combustion, or it's too lean, and above 46%, there's too much fuel and not enough air to support combustion, or in that case, too rich. These are referred to as the upper and lower explosive limits, or the UEL and LEL. This large combustible range makes H2S potentially dangerous. Now that we know about the dangers of H2S, it's important to understand where it comes from. H2S is typically the byproduct of biological activity involving sulfur-reducing bacteria, or SRBs, on organic matter. However, H2S can also form from organic matter where significant heat is present by thermal reduction of sulfate and/or other sulfur-containing molecules. In oil and gas production, H2S comes from underground reservoirs where plant and animal matter was trapped millions of years ago and through elevated temperature and pressure was eventually reduced to crude oil and natural gas. Exposure in these scenarios are typically through exploration, primary treatment, transportation, and refining. SRBs may also be introduced back into the reservoir by injection of fresh water during drilling and completions operations or during production for pressure balance or enhanced oil recovery. H2S can also form in storage tanks, rail cars, tank trucks, pipelines, etc., wherever SRBs are present. And lastly, H2S is found where organic matter is decomposing, such as in bogs, landfills, etc. So next time you are on a hike in the woods and you smell rotten eggs, there's likely a bog nearby, or at least some rotting organic matter. The terms sour and sweet mean different things depending on where you are involved in the oil and gas industry. On the natural gas side, sour means it contains greater than or equal to 4 ppm of H2S on a mole basis. Sweet means it contains less than 4 ppm of H2S. That doesn't mean that natural gas doesn't smell bad and contain other types of sulfur compounds. In fact, natural gas sold to the public actually has 2 organic sulfur compounds added as an odorant to make sure that it can be easily detected in the event of a leak. Only H2S, however, is considered when designating natural gas as sour or sweet. Crude oil, on the other hand, is different. Sour means it contains greater than or equal to 0.5% or 5,000 ppm total sulfur on a mass basis. Sweet means it contains less than 0.5% or less than 5,000 ppm total sulfur. In crude oil, H2S is generally only a minor component that makes up a very small proportion of the bulk, typically in the 1 to 200 mg per kilogram or 0.0001 to 0.02 mass percent range. The remaining sulfur is bound within large organic molecules such as mercaptans, asphaltenes, polysulfides, and aromatics. You may have also noted the difference in the units used between natural gas and crude oil. Natural gas is measured on a molar or volumetric basis, which for gases are equivalent. In these units, 4 ppm equals 4 moles of H2S in 1 million moles of natural gas, or volumetrically 4 milliliters of H2S in 1 cubic meter of natural gas. Crude oil is measured on a mass basis. In these units, 0.02 mass percent equals 0.02 grams of H2S in 100 grams of crude oil, which is also equivalent to 200 weight ppm, which equals 200 milligrams of H2S in 1 kilogram of crude oil. These units cannot be compared directly, so pay close attention to what the units are based on. ppm is often used generically and frankly can be very confusing to interpret because it can be used in multiple contexts with varying combinations of units. For example, in gas, ppm on a molar basis is the most common. In crude oil, ppm on a mass basis or milligram per kilogram is the most common. However, in water, ppm on a mass to volume basis or milligram per liter is the most common. In 2019, the CCQTA published a white paper regarding sour versus sweet designations to provide a document to help industry and government educate their staff on the differences. This document is currently available on the CCQTA website under the Publications menu. Why, as a technical organization, did the CCQTA get involved with H2S? It all started for the CCQTA with an oil tanker stranded at sea with no port willing to accept its crude oil cargo because of the H2S testing results. When the cargo was loaded at the departure port, one testing method was used on the crude, and that method reported in ppm by mass and met the specification of the receiving port at the time. When the cargo arrived at the receiving port, it was tested again using a different method that measured the H2S in the headspace above the crude and reported in ppm by mole. The headspace results were well above the H2S specification value they would accept. That situation would eventually be resolved between the parties, however it brought the issue of differing H2S measurement methods and reporting units to the CCQTA's attention. At a similar time as the tanker incident, NACE revised the MR0175 material standard and removed a legacy exclusion. This clause was for transmission pipelines in relation to the material requirements for sour service operation to prevent sulfide stress cracking, or SSC. This prompted the Canadian Standards Association, or the CSA, to also update standard CSA Z662 to which Canadian pipelines must adhere. With thousands of kilometers of transmission pipelines already in service that were not constructed to sour service specifications, this caused a lot of concern for pipeline operators. CSA Z662 included a clause that pipelines needed to be operating below 0.3 kPa, around 2700 ppm by mole, H2S in the gas phase at the bubble point. A consortium of Canadian transmission pipelines did significant independent work starting in 2009 to identify a testing methodology or an accurate, more capable method of determining the H2S concentration in the vapor phase at the bubble point. However, it was deemed too onerous and impractical on an ongoing basis. These two concurrent activities launched 3 CCQTA projects. H2S measurement in crude was initiated to evaluate the available test methods associated with H2S measurement with the intent to educate the industry on the fit for purpose of each one. This project is now closed, and the report of the findings is available on the CCQTA website under the Publications menu. H2S PVT was intended to develop a methodology to measure H2S at the bubble point. This project eventually transitioned from bubble point measurement to the development of an analyzer for accurate measurement of H2S in the vapor phase under controlled sampling and analysis conditions. This project is still active today. And lastly, pipeline sour service. This project was started to challenge the science behind the revision of NACE MR0175 through physical SSC testing and transmission pipeline experience. The project group successfully lobbied the NACE MR0175, ISO 15156 Maintenance Panel, and the TG299 Technical Oversight Committee to reintroduce the exclusion clause for transmission pipelines. The extension of that work is to have the CSA Z662 also revised to reflect a transmission pipeline exclusion. We have introduced the idea of testing methods, reporting units, and results interpretations. However, one critical element we have not discussed yet is sampling methods that are impact on testing and results. H2S measurement is tricky. The first step to any good measurement is to capture a good sample. However, the properties of H2S also pose some unique challenges to capturing a sample. H2S is a gas, it is also reactive, UV sensitive, and as discussed, toxic. It also has a nasty tendency to stick to metal surfaces. Typically, that either means capturing a sample in the field and testing it immediately, or preserving it so it can be transported to a lab for analysis while maintaining the integrity. A good sample leads to a good result, and a poor sample leads to poor results. Often we use the saying, junk in equals junk out. This saying is also not limited to lab work. It simply means bad inputs lead to bad outputs. For H2S, there are some specific practices that we want to employ to minimize issues with sample integrity. Firstly, H2S is a gas, so understand that even in a liquid sample, the H2S is only dissolved and will readily escape given the opportunity, especially with changes in pressure and temperature. This goes back to our previous lunch and learns on vapor pressure. There are two types of sample containers to capture a sample: an atmospheric or open container, or a sealed container. You can see the difference between the two in that evaporating or gaseous molecules in the open container are not restricted from leaving, and in the sealed container they are restricted. Just that simple. Let's start with the open container. This type of sample is taken directly off the process into a bottle or can at atmospheric pressure. Note that both types are intended to prevent UV light from contact with the sample within. An atmospheric sample from a hot process, such as a treater intended to degas crude oil in order to decrease its vapor pressure, will have a tendency to also lose H2S quickly. To minimize this, the sample should be cooled prior to entering the sample bottle or can. While this works well for light hydrocarbons such as pentane or hexane, gaseous components that have very high vapor pressures are less impacted, and some or all may still be lost during sampling. Also, note that the sample is introduced to the bottom of the bottle to minimize agitation that also may result in H2S loss from the sample. How about sealed containers? This type of sample is taken directly off the process into a sealed cylinder. This type of sample container is ideal for sampling where dissolved or gaseous H2S is involved because there's no opportunity for H2S to escape. There are a few options for a sealed container. Firstly, the floating piston cylinder, or FPC, which requires a sample point to have sufficient pressure to move an internal piston and displace a pre-charged fluid, which is typically air or nitrogen. Next is the manual piston cylinder, or the MPC, which is intended for low-pressure sample points such as tanks or rail cars and allows the user to pull the piston back manually to draw sample into the cylinder. And lastly, we have the constant volume cylinder, commonly referred to as a sample bomb. This is a simple cylinder with valves on either end to contain the sample within. One thing to note is that H2S tends to stick to stainless steel, reducing the apparent concentration of H2S in the sample. Aluminum cylinders are more suitable for H2S samplings. This tends to be more of a problem for gas sampling as opposed to liquid sampling. Now that we've captured a sample, what are the options for testing methods? There are three common testing methods used for H2S. ASTM D5705, ASTM 5623, and UOP 163. There is also a fundamental difference in how these report H2S. ASTM 5705 reports the H2S content of the vapor phase above a crude oil, while the other two methods report the H2S content of the liquid phase. Liquid and vapor results are not equivalent or comparable, and I'll explain why in a moment. First, let's describe the basic premise of each method, starting with ASTM D5705. 500 milliliters of crude oil is transferred to a 1 liter bottle, and then the vapor space is purged with nitrogen to displace the air. The bottle is then sealed with a stopper, which includes a thermometer immersed in the liquid. The bottle is then placed in a 60 degrees Celsius water bath for 30 minutes or until the temperature reaches 60 degrees Celsius. The bottle is then removed from the water bath and rigorously agitated for 3 minutes. Now comes the exciting part. Quickly remove the stopper and immediately cover the bottle with aluminum foil. Insert a length of stain detection tube through the foil. Extract a sample of the headspace vapor by pulling volume through the tube using the supplied hand pump. Typically, this pulls 100 ml of the sample vapor through the tube. Lastly, read the tube to obtain the H2S content of the vapor in ppm by volume or by mole. Under those conditions, that is the H2S content of the vapor phase. As you can see, it's a relatively simple test, however there are some pitfalls. Firstly, the method was intended for very low vapor pressure residual fuel oil, which has a vapor pressure around 10 kPa. So using an open sampling method followed by an open testing method is relatively reliable. Crude oil, on the other hand, has a pipeline vapor specification ranging from 69 to 103 kPa at 38 degrees C. That means as soon as the crude is open to the atmosphere, there will be evaporative loss. The simple act of transferring the crude first to the sample container and then the test bottle provides ample agitation to cause loss. This simple animation highlights the sloshing and agitation effects of filling a sample bottle. Secondly, the test heats the sample to 60 degrees Celsius, so that increases the vapor pressure even more. Although the test bottle is sealed with a stopper during the heating step, the stopper is removed and is replaced with foil and then agitated. Both of these activities are further opportunities for loss. Next, since the H2S content of the vapor space is typically unknown when taking the measurement, it's possible that the H2S level is off scale for the first detection tube. In that case, another tube or tubes need to be used and a further 100 ml of headspace vapor needs to be sampled. That leads to dilution of the headspace and a reduced apparent H2S content. Lastly, this method reports the vapor space concentration under specific vapor-liquid conditions of 1:1. The vapor phase of H2S under these conditions cannot be easily translated to other vapor-liquid conditions. I'll explain this in a little more detail later. ASTM D5623 is a sulfur-specific gas chromatography method used to quantitate individual sulfur species, including H2S in the liquid phase. This method can be set up to accept either atmospheric or pressurized samples. The gas chromatograph performs a separation of the sulfur species based on their boiling point, and then the individual sulfur species are combusted in a hydrogen-oxygen plasma to form sulfur monoxide. The sulfur monoxide is then contacted with ozone, O3, forming SO2 in an excited stage, which immediately releases a photon and goes back to the ground state of SO2. That photon is detected and the signal plotted. Since only sulfur-containing species will form the initial sulfur monoxide, the detection method is sulfur-specific. This is a high accuracy method with few interferences, however it also tends to be the highest cost since the chromatography and detector systems are very expensive. This method is best used when speciation is required to identify other species or in the event of a dispute. This method reports results on the whole crude on a mass basis in milligrams of H2S per kilograms of sample. The last method we're going to look at is UOP 163. This method is intended for open samples but can be modified to accept pressurized samples. This is a relatively simple titration method for H2S quantitation. Sample is transferred to a beaker and then weighed, and then a solvent solution of alcoholic ammonium hydroxide is added. The H2S in the sample reacts with the ammonium hydroxide and is converted to water and ammonium sulfide. Since ammonium sulfide is an ionic salt, it remains in the solution, so there is no concern for loss after contact. That mixture is then titrated potentiometrically with alcoholic silver nitrate using a silver-silver sulfide electrode. The potentiometric curves look like this. The different inflection points are used to calculate the volume of titrant, and the H2S concentration is calculated. Note that the inflection point changes depending on the presence of other mercaptans and disulfides. At the start, I mentioned that this method could also be adapted to accept pressurized samples. The first animation shows the method as we just described, with the sample simply being introduced to the beaker before the solvent is added. The second animation shows the beaker with the alcoholic ammonium hydroxide solvent pre-filled, and then the sample is introduced slowly below the level of the solvent solution. Any H2S that evolves from the crude oil will immediately contact and react with the ammonium hydroxide, fixing it in the solution. Like the method as written, once the crude is in the solution, the beaker is weighed and the mass of crude is recorded. Now that we understand how the methods work, let's compare the units the results are reported in. As you may have noticed, ASTM D5623 and UOP 163 report results on the whole crude on a mass basis in milligrams of H2S per kilogram of sample. These results are not comparable to vapor phase results from D5705 for two reasons. First, as I mentioned, D5623 and UOP 163 are reported on a whole sample basis and not the vapor phase like D5705. Secondly, the units of measure are very different and represent different phases entirely. Let's look at the different phase measurements practically. D5623 and UOP 163 give you the milligrams of H2S per kilogram of crude oil. As a worst case scenario, you could say that what if all the H2S came out of the liquid and was released? That's a relatively easy calculation. For example, if you have 1 kilogram of crude that has 100 milligrams per kilogram of H2S, that equates to 100 milligrams of available H2S for evolution. On the other hand, if you have similar D5705 results, you know that at 60 degrees C and a 1:1 VL ratio gives you a vapor space results of 100 microliters per liter of H2S in the vapor space. If you made the same assumption that during the measurement all of the H2S in the liquid was evolved into the vapor space, that would equate to only 0.18 milligrams of H2S that was measured in the vapor phase, which would translate into 0.18 milligram per kilogram in the crude oil. What I'm really trying to highlight is that those are obviously very different outcomes between the results when put into context. Let's take those results and see what the impact on the ambient concentration would look like. Using the liquid phase measurement, we found 100 milligrams of H2S in our 1 kilogram of crude, and using the vapor phase measurement, we found 0.18 milligrams of H2S in our 1 kilogram of crude. Using those values, in the same 10 by 10 by 8 foot room we used previously, we see that the concentration of H2S in the room is 2.9 ppm and 0.005 ppm respectively. That is a significant difference. In this example, neither are dangerous concentrations, however it shows how the results could easily be misinterpreted. What I'm really trying to highlight is that those are obviously very different outcomes between the results and when put into context. In this example, we looked at two sets of crudes, both showing 100 ppm H2S tested by different methods. One on the liquid phase and the other on the vapor phase, and how those could be interpreted into a real-world concentration. Liquid phase measurements are absolute because they consider the mass of H2S as part of the whole sample mass. Vapor phase measurements are not absolute because they're dependent on the vapor-liquid ratio and the test temperature and only report on the evolved vapor. One additional consideration is the interaction of H2S with the liquid composition. A typical crude oil composition contains hundreds to thousands of different components. Some of those hydrocarbons have no affinity for H2S, while others have a strong affinity for H2S and tend to hold on to it. That impacts how much H2S can evolve into the vapor phase for measurement. Since it's virtually impossible, or at least impractical, to identify all different hydrocarbons in a crude oil, that means it's not possible to determine how much H2S would be released into the vapor phase based on the concentration of H2S. Simply put, you can't determine the H2S in the liquid from vapor phase results, and alternatively, you can't determine the amount of H2S in the vapor phase based on the liquid phase results. This is why the two types of results are not directly comparable. In my previous example, I made the assumption that all the H2S would evolve from the liquid phase as the worst case scenario. In reality, the amount of H2S that partitions from the liquid into the vapor phase can be anywhere from about 8 times to as much as 30 times. Keeping in mind, we're going from a mass measurement to a volumetric or a molar measurement. Let's look at a similar example using the 100 mg per kilogram H2S in crude oil based on the liquid phase results as a starting point. If ASTM D5705 was performed with that same crude oil, the vapor phase results could range anywhere from 800 ppm to 3000 ppm by volume or by mole. That's a pretty significant difference. This is what originally caused the problem with the crude stranded at sea. That crude was tested by UOP 163 at the loading port and had results that met the specification. However, when it reached its destination, it was tested again using ASTM D5705, and the results were significantly higher, as we've just talked about. Since the new H2S results didn't meet the receiving port's requirements, it was rejected. I hope that puts some context around H2S measurement and the difference in units and why it's very important for you to pay attention to the units when you're looking at results. At this point, we have looked at the properties of H2S, the sampling and testing methods available, and the interpretation of results based on the units of measure. Now we'll look at the ways H2S is managed or controlled in the industry. There are a few ways to control exposure to H2S, similar to any other hazard. Engineering controls, administrative controls, and lastly, personal protective equipment. Engineering controls are the physical systems put in place to prevent release of H2S containing fluids with the ultimate goal of preventing exposure to employees and the public. These include alarms, vapor recovery systems, ventilation, etc. Administrative controls are the policies, procedures, and training programs companies put in place to instruct and guide people on how to handle fluids that contain H2S. And lastly, personal protective equipment is the last line of defense when the other two have failed. There's an additional method of engineering control that gets used regularly. That is a chemical treatment to either bind H2S so it cannot evolve or to react it so it no longer exists as H2S. These are referred to as H2S scavengers. While on the surface these appear like easy solutions, there are downstream consequences to the use of these chemistries. Let's look at the two most common classes of chemicals for H2S treatment: ethanolamines and triazines. Ethanolamines have both amine and alcohol functional groups. Monoethanolamine, or MEA, and diethanolamine, or DEA, are the most common in this class. Triazines are characterized by their hexagonal ring structure containing 3 nitrogens and 3 carbons. These are further differentiated by the addition of either hydroxyl or methyl groups on the 3 carbons. These make MEA triazine and MMA triazine. We're going to focus on ethanolamines for a moment. Ethanolamines have a particular solubility for H2S, and it is used heavily in the upstream sector to remove H2S from natural gas. MEA can hold about 15 weight percent H2S. This is a simple diagram of an amine gas sweetening process. H2S-rich gas enters the approximately 40 degrees C amine contactor near the bottom and contacts lean amine running down from above. As the gas contacts the liquid, the H2S is absorbed into the amine solution, and the H2S-free gas leaves from the top of the tower. The rich amine then passes through the regenerator, where it is heated to 120 degrees Celsius to release the H2S, and then the lean amine returns to the contactor.
Where DEA and MEA can be problematic is when they're used in crude oil production, midstream, and/or transportation operations to control H2S. In the gas scrubbing example, we just looked at how the amine is simply recycled, so it never ends up in the final product. However, MEA and DEA can be used as an H2S scavenger in crude oil applications, simply by mixing it with crude oil. This may be done in storage tanks, trucks, rail cars, etc. In that scenario, it remains with the product and travels with the crude to the refinery. This diagram shows many of the points along the way that scavenger can be added to the crude oil, as well as a few points where dilution can take place. You'll notice that transmission pipelines and refineries are not points where scavenger is added. This is because there is no risk to the refinery because they routinely deal with H2S generation as part of a crude refining, so having it in the feed is no problem for them. Production and gathering pipelines are at risk of sulfide stress cracking due to the presence of H2S because they're commonly in 3-phase flow with gas, liquid, and water all present together. Transmission pipelines, on the other hand, are in 2-phase flow with only crude oil and water, therefore any H2S present is dissolved in the crude. The water content of transmission pipelines is also very low comparatively, so the conditions that promote SSC do not exist here. H2S does not promote a risk to transmission pipelines infrastructure. With that in mind, scavenger is not required for either refinery or transmission pipeline applications. As I mentioned, production gathering systems are at risk from H2S, so scavenger use is appropriate for these applications. However, the type of scavenger used is important to consider. Other areas where scavenger is also added are truck, rail, and marine loading. In these applications, scavengers are generally used for EH&S purposes to protect those handling the products where potential for exposure is likely the highest. We've discussed ethanolamines and their typical role in H2S removal from natural gas in a regenerative loop. They're not suitable for applications where they will persist in the product all the way to the refinery.
In these scenarios, the triazine-based scavengers we discussed earlier are better suited. This type of scavenger reacts with H2S to eliminate it entirely. Let's look at the reaction mechanisms of these two commonly used triazines, starting with MEA triazine. One MEA triazine molecule reacts with 3 H2S molecules to form one triethane molecule and 3 MEA molecules, so the H2S is gone and is no longer a risk. The downside of this is that while the user did not put MEA into the crude directly, the reaction generated MEA anyways. This newly formed MEA is now on its way to the refinery. Now in reality, the reaction has several intermediate steps where MEA triazine reacts with one H2S and then forms thiazine, and then reacts with another H2S to form dithiazine, and lastly with one more H2S to form triethane. The reaction typically does not go all the way to the completion, so it generally forms more dithiazine than either of the other two forms. MMA trizene has a very similar mechanism with the similar intermediate steps as MEA trizene. However, the byproduct is methylamine as opposed to MEA. Let's get into why all this matters to refiners. Once at the refiner, amines go two directions. First, the crude is contact with wash water in the desalter, and given that amines are highly water soluble, the majority ends up in the water phase. Any remaining amine is carried with the crude into the atmospheric crude tower. However, amines are problematic in both areas. In the wash water, ethanolamines are toxic to aquatic life and kill the good bacteria used in the wastewater treatment process, causing upsets and the potential for water quality issues, hence additional treatment is required. Trizene and dithiazine are both biodegradable, so they have limited impact. However, just like we talked about, the MEA trizene reaction produces MEA, so the toxicity is similar. In the atmospheric crude tower, available salt can hydrolyze and form hydrochloric acid, which travels into the crude tower overhead system. When HCl contacts MEA, a liquid amine salt is formed. This very corrosive salt results in corrosion to trays, heat exchangers, and piping in the overhead circuits. The resulting corrosion is very costly and in many cases requires the refinery to shut down for repair. Methylamine, on the other hand, forms a less corrosive salt, so MMA trizene is favored over MEA trizene. These are examples of what overhead corrosion due to amine salts looks like. First, we have a photo of corrosion penetration in an overhead condenser tube. Next is the tube side of an overhead pump round bundle. And lastly, corrosion inside an overhead pump round line. In 2019, the CCQTA published an information bulletin called H2S Scavenger Use in Crude Oil, Factors Affecting the Selection and Use of H2S Scavengers. This was intended to provide guidance to industry on the types and uses of scavengers and provide background on what the downstream implications of scavenger use are. One of the key messages was to avoid overdosing scavenger by dosing based on the concentration of H2S in the crude. Another consideration is the contact and reaction kinetics between the crude oil and the scavenger. For a scavenger to be effective, it must contact the in situ H2S and also have time for the reaction to take place. Simply pouring a pail of scavenger into a rail car or tank truck may or may not serve the intended purpose of lowering or eliminating H2S. The scavenger needs to contact the dissolved H2S, therefore proper mixing is essential. Many assume that the movement of the fluid in transit is often enough to provide mixing energy. However, it is generally not sufficient since baffles are typically in place specifically to limit sloshing. For example, an operator samples a product and finds the H2S levels too high, so they dose scavenger directly into the railcar and then retest the product for H2S. This simulation shows an empty railcar dosed with a pail of scavenger. You can see it settles on the bottom of the railcar. However, when the crude is added to the car, the scavenger is mixed directly with the incoming crude. In this case, there has likely been reasonably good contact, so the H2S content has also likely been reduced. Do keep in mind the time component of the reaction, and testing immediately after filling may provide an inaccurate result. This second example shows the same railcar, however the crude is loaded first and then the scavenger is added after. Since the car was already loaded and there's limited turbulence or agitation in the car at this point, it is likely that the scavenger and crude contact is poor. In this case, there's also a good chance the product will still have high H2S when tested. That may prompt the operator to continue dosing and retesting until the product is below their specified limit. At that point, the operator could have overdosed the product by many times. Ideally, had the scavenger been mixed with the product upstream of loading, there would have been vastly improved contact and the resulting retest would have showed a decreased H2S level with much less scavenger required. Similarly, the operator may have simply calculated how much scavenger was required and dosed the railcar and sent it on its way. The product may not have been mixed during transit, so the H2S level in the product would be higher than the receiving operator is expecting, so they may not have taken the appropriate precautions. Let's summarize what we've talked about today. First, we looked at the basics of H2S, including the chemical structure, the associated hazards, the origins and locations where one might find H2S, and lastly we did a comparison between the different definitions of sour and sweet between the oil and gas sectors. Next, we looked at how the CCQTA got involved with H2S, starting with external activities impacting the industry and bringing it to the CCQTA's attention, and then a brief description of the CCQTA projects that were initiated in response. Next, we looked at H2S measurement, which included sampling methods and how they might impact further analysis, a description of the 3 most commonly used testing methods, then a discussion on the interpretation of results and specifically around the units of measure each method reports, and then that was followed by a couple of practical examples highlighting how the results could be misinterpreted. Lastly, we looked at H2S control, including a high-level look at how hazards are managed, the specific chemistries that are used for H2S control, and the downstream implications of those chemistries, and then finally a couple of examples of scavenger dosing. That's it for this episode. Thanks for watching, and I look forward to connecting again. If you would like further information about this topic or any other topics the CCQTA is working on, please visit our website at ccqta.com. If you have any specific feedback, please send it to secretary@ccqta.com. Please check back regularly for new additions to our Lunch and Learn series and other videos.